Our topic of discussion today is work, energy, and power. So, this is quite a sizable topic, so I'm going to break it up into a few videos that hopefully you should watch before our class on Sunday. That way, you are able to keep up with Sunday's class, whereby we will cover a few examples and questions, and hopefully, if there is enough time, we'll have a look at a few past paper questions. Let's start. Work, energy, and power. Let us start by defining work. So, work done is defined as the product of the force and the displacement in the direction of that force. So, let's have a look at this formula. That W represents the work done on an object. F represents any force. We can have applied force in there, gravitational force, normal force, frictional force, or even tensional force. Whereas displacement represents the change in position of the object or the distance that that object covers. And our cos theta, that's where most students struggle. So theta represents the angle between our displacement vector and our force. So we'll have a look at a few examples whereby we'll try to figure out the value of theta, and hopefully that should clarify or fill in the gaps wherever there's a bit of a misunderstanding. So let's start with an example. So we have this object on a rough horizontal plane, and let's say there is a 50 Newton applied force that is acting on this object. So someone is pulling this object or pushing this object towards the right. So if someone is applying a force in the right direction, that means our object is going to move in the right direction or towards the right. So if our object is moving in the right, that means our displacement is also going to be to the right. So let us draw a displacement vector moving in the right direction. Now, in addition to applied force, we know that this object has a mass, therefore, it's going to have a gravitational force, and it is on a surface, therefore, it's going to have a normal force as well as a frictional force or kinetic frictional force. Now, if we want to calculate the work done on this object, what we are going to do is we're going to break it up. Let's start by calculating the work done by each individual force, and then we can have a look at how we will calculate the work done or the net work done. The net work done is the work done by all the forces, or you can think of it as the resultant work or the total work done on this object. So let's start. Let's say this object has a displacement of 5 meters, and let's say there is a mass of 10 kgs. Let's give this a frictional force of 20 newtons. So let's start by calculating the work done by each individual force. So first we'll start with the work done by applied force, followed by the work done by frictional force, normal force, and finally the work done by gravitational force. So let's have a look at our first one, which is the work done by the applied force. So question number one, let's put in our formula. And because we are calculating the work done by applied force, we can add our subscript FA to indicate that this is the work done by applied force. And by our force, we can add the subscript A to denote that this is the applied force. Now, something important to take note of is that when we are dealing with work, which is a scalar quantity, we do not need to include the direction in our force. I know that it's something that we normally take into consideration. We're always trying to identify whether this force is positive or negative based on its direction. But due to the fact that work is scalar, we don't need to take it into consideration. So, what we are going to do is we are only going to substitute the magnitude of our force. We are not going to substitute the positive sign or the negative sign. We are only going to substitute the magnitude. The value of our applied force is 50 newtons. So we'll substitute 50 times the value of our displacement, which is 5 meters, times cos of the angle between our displacement and our applied force. Now, how do we figure out the angle between our displacement and our applied force? So let's start by drawing a free body diagram of our object. So we know that the displacement is moving to the right. So we'll draw our dotted vector for displacement, and let's draw the vector of our applied force. Now, as you can see, our applied force and our displacement are moving in the same direction, and they're kind of just next to each other or on top of one another. So you can see that there's no space in between the two vectors. So there's an angle of 0 degrees. If there were space between the two, this is what it would look like. So this space here would be our angle theta. But because our force, or rather our applied force, and our displacement are on top of one another and moving in the same direction, we say that there is no space between them. So there is an angle of 0 degrees between them. And this will then give us a work done by applied force as 250 joules. Now you can see that is a positive value. So what does that mean? What does it mean to end up with a positive work value? If we end up with positive work, that means energy is being transferred into the object. Because keep in mind that work is not a vector quantity, which means it does not have direction. So we cannot say 250 joules right or 250 joules left. We would say 250 joules of energy has been transferred into our object. Now, let us have a look at the work done by frictional force. So we'll add our subscript. Now keep in mind the formula is always the same. Work is equal to the force times the displacement times cos of theta, whereby theta represents the angle between our displacement vector and our force. So the only difference between them is the subscript, so that we can denote or specify what work we are calculating, whether it's the work done by the applied force or the work done by our frictional force. So once again, work is a scalar quantity, therefore we are going to substitute the magnitude of the forces, not the positive or negative signs. So we know that the frictional force or kinetic frictional force is 20 newtons times our displacement of 5 meters times cos of the angle between them. Now, let's go back to our free body diagram and put in our kinetic frictional force vector. So, as you can see, kinetic frictional force is parallel to our displacement but moving in the opposite direction. And if you notice, there is a 180-degree angle between them because this is a straight line. So, this is going to be 180 degrees. And if we put this into our calculator, we would end up with negative 100 joules. So whenever we end up with a positive work value, it is because energy has been added to the object. Whenever we end up with a negative work value, it is because energy has been removed from our object. So in this case, 100 joules of energy has been removed from this object. Now let's move on to number 3. Let us calculate the work done by our normal force. Now, something important to take note of about normal force is that our normal force is equal to our gravitational force. So the way we would calculate normal force is by multiplying the mass times the gravitational acceleration. So our normal force is going to be mass times gravitational acceleration. So our mass is 10 kgs times our gravitational acceleration of 9.8 times our displacement of 5 meters times cos of our angle. Now, what is the angle between our normal force and our displacement? So something important to take note of is that normal force is the force that acts perpendicular to the direction of motion, and displacement represents our direction of motion. So, in another way, or in a different way of speaking, we can say that normal force is the force that acts perpendicular to our displacement. So that means that there is an angle of 90 degrees between our displacement and our normal force because they are perpendicular to one another. So if we were to add normal force in here, we then conclude that normal force is perpendicular to our displacement, therefore it has an angle of 90 degrees. And if you put in 10 times 9.8 times 5 times cos of 90 into your calculator, you would end up with a value of 0 joules. The reason is that cos of 90 is 0, and anything times 0 is 0. So whenever your force is perpendicular to your displacement, such as normal force, you would end up with a value of 0 joules, which means that there is no energy being added to the object and there is no energy being removed from the object. No work is being done by the normal force. Now, let us have a look at the work done by our gravitational force Fg. Now, what is the value of Fg? How do we calculate Fg? We know that Fg is calculated by multiplying the mass times the gravitational acceleration. So, sub that in. Mass times gravitational acceleration. Our mass is 10 kgs times our gravitational acceleration of 9.8 times our displacement of 5 meters times cos of the angle. Now, what is the angle between FG and displacement? So let us add to our free body diagram. This is going to be force Fg. Now we can see that normal force and Fg form a straight line. That means that Fg is also going to have a 90-degree angle between displacement and Fg, which means that Fg is perpendicular to displacement when the object is moving on a horizontal plane. So this is also going to be 90 degrees. A quick calculation to show that is the angle of normal force plus the angle of Fg equals 180 because it's angles on a straight line, and because we've already proved that normal force is 90 degrees, we can now calculate the angle of Fg. So if you were to move 90 degrees to the right, that would then be the angle of Fg equals 180 minus 90, which would then be 90 degrees. Now, another way of thinking about it is just to look at Fg and displacement. You can see that they are at right angles to one another. So the angle between them is going to be 90 degrees. Now, someone might wonder, why did we go in the clockwise direction for Fg, whereas in all the other examples where it was applied force, normal force, and kinetic frictional force, we went in the anti-clockwise direction. The reason is that you can move in the anti-clockwise direction and you would end up with 270 degrees. Now, if you put cos of 270 degrees onto your calculator, it will also give you 0. And cos of 270 degrees is the same thing as cos of 90 degrees. So you can use either or. An easier way is just to see which is the shortest distance between displacement and Fg. So that would be to move in the clockwise direction. And if we move in the clockwise direction, we would end up with a negative force. Sorry, a negative angle, not negative force. So cos of negative 90 is the same thing as cos of 90 because cos is positive in the fourth quadrant. So either way you look at it, it's still going to be a 90-degree angle between Fg and displacement. And that is then going to give us 0 joules. So we have now calculated the work done by applied force, frictional force, normal force, and Fg. Let us add one last question to this example. Let us calculate the net work done on the object. Now, net work is also referred to as the total work done on the object. There are two ways of calculating net work. Firstly, we can add up all the individual works that we've calculated, and that will give us the net work done on the object. Alternatively, we can use the formula work net equals F net times displacement times cos of theta, where F net is calculated by adding up all the forces that are acting on this object, taking into consideration the direction of those forces because we are calculating F net, which is a vector quantity. And our theta value would represent the angle between our displacement and our F net value. So let's start with method 1. So as previously discussed, Method one is to add up all the individual works, and that will give us the net work done on the object. So our formula is work net equals the work done by our applied force plus the work done by our kinetic frictional force plus the work done by Fg plus the work done by our normal force. Now, if we add all of that up, that is going to then be positive 250 joules plus negative 100 joules plus 0. And that will therefore give us the net work done as positive 150 joules. So the net work done on this object is positive, which means that the net work is adding energy to the object. Now, our second method. Now, method two involves calculating F net. So let's start by writing out our formula. So the second method makes use of the formula work net equals F net times displacement times cos of theta. So if you notice, the second method is just basically the normal formula that we are used to. Work equals the force times the displacement times cos of theta. But now, because we're using the net force, we'll be calculating net work. So let's start by calculating our net force. So net force is equal to the force of our applied force plus our frictional force, and that is then going to be equal to, before we actually substitute our values, let's first go and see what are the directions of our forces, because keep in mind that because we are calculating F net, which is a vector quantity, we need to take into consideration the directions of our forces. So our applied force is 50 newtons to the right, whereas our kinetic frictional force is 20 newtons to the left. So I'm going to take my direction of motion as positive. So I'm going to take applied force as positive 50 newtons because it is in my direction of motion, and opposing the direction of motion is my kinetic frictional force, which is then going to be negative 20 newtons. So this is going to be positive 50 plus negative 20, and that will therefore give me my net force as 30 newtons. Now, because my net force is positive, that means that it is in the right direction. So let me substitute into my formula. So F net is 30 newtons times my displacement is still the same, 5 meters times cos of my angle. Now, theta represents the angle between my displacement, and in this case, because I'm calculating work net and I'm using F net, my theta value is the angle between my displacement and my F net force. So let us draw a dot to represent the object, and my displacement is still in the right direction. And as we can see, we obtained a positive value for F net. Therefore, my F net value is going to be in the right direction. And as you can see, there is an angle of 0 degrees, between F net and displacement, similar to what we had with applied force and displacement when we are calculating work done by applied force. Because both vectors, or because both are moving in the same direction, and they are parallel to one another and basically on top of one another, there's a 0 degree angle between them. So my theta value is going to be 0 degrees. Therefore, we can conclude that work net is equal to 150 joules. Now, as you can see, we obtained the same value in both methods. So let's just do a quick recap on what we actually did in method 1 and in method 2. So within method 1, all we did was we added up all the individual works and got our net work. Now, something important to take note is that we do not include, or we do not take into consideration, the directions of the forces when calculating for method 1. All we do is we just add up the individual works that were calculated in the previous question, or in the previous questions 1 to 4. Now, let's have a look at method 2. So for method 2, all we did was, because we are calculating work net, we use F net. Similar to how when we calculated for the work done by the applied force, we used applied force. So in this case, we're calculating the work done by the net force, or in other terms, we are calculating work net, we use the net force. Now, something important to take note of here is that when we are calculating for the net force, we take into consideration the direction of the forces. When calculating net force, because it is a vector. Now, our angle theta represents the angle between our net force and our displacement. Let us do one more example before we end our video for today. So in this particular example, we are dealing with a force that is inclined, or that is at an angle to the horizontal, specifically a 30-degree angle. So how will we deal with our applied force, and how will we calculate the work done by that applied force when it is at an angle? So let us start by putting in a few additional forces. Let us have the force of gravity, or Fg, our normal force, and our force of friction, or kinetic friction. And let us put in our displacement. And let's say this object has a mass of 10 kgs and a displacement of 5 meters. So, how will we calculate the net force done on this box? So as we mentioned previously, there's two methods. the first method is to calculate the individual works, add them up, and that will give us the net work. The second method is to calculate the net force and then use our formula work net equals F net times displacement times cos of the angle between our displacement and our net force. So let us first use our method 1, whereby we calculate the individual works done by each individual force and add them up. Keep in mind that when we are dealing with our first method, we do not take into consideration the direction of the forces. We only take into consideration the magnitudes, not their directions, so we will ignore the positive and negative signs of our forces, which means that we will not substitute them into our formula because we are calculating a scalar value, which is work. Start by calculating the work done by our applied force. So our formula is work equals our force times displacement times cos theta. Because we are calculating work done by applied force, we can add our subscript, and let us now substitute our value for our applied force. Let's give our applied force a value of, let's have it as 50 newtons, and let's have our kinetic frictional force as 20 newtons. So, because we are only taking the magnitude and not the direction of the force, we are going to substitute positive 50 times our displacement of 5 times cos of our angle. Now, we need to figure out what is the angle between our displacement and our applied force. So as you can see from here, this is our displacement and this is our applied force, and you can see that there is an angle of 30 degrees. Now, something important to take note of. You should be used to breaking up angles at an incline into their components, the perpendicular and parallel components, or you can call it the X and Y components. Now, if you look at the applied force, it is at an angle, and if we were to break up this force that is at an angle, so let's redraw it over here. So this is our force, and if we were to break it up into its components, we would have F A in the y direction and FA in the x direction, and this is our 30 degrees and 90 degrees. Now, if we wanted to calculate the horizontal component, which is FAX, because it is in the adjacent side, we would use the value of our applied force times cos, because cos deals with the adjacent side of 30 degrees. Now, if you notice here, technically we are using that because the formula already incorporates that into it. So we don't need to use all of this extra calculation and do all of this extra work because the work formula already does that for us. All we need to do is substitute the value of the applied force irrespective of whether it is horizontal or at an angle. So let us substitute our value of 50. Keep in mind that we do not substitute the direction, we only substitute the magnitude because we are calculating a scalar value, which is work. Now, before we continue, let's take a moment to draw our free body diagram. So when we draw a free body diagram, the object is represented by a dot. Let us also include our displacement. Let us put in our force, which is our applied force, and the angle between it, which is 30 degrees. So based on this, you can also see that the angle between our displacement and our applied force is 30 degrees once again. So this is the first part of our free body diagram. Let's put in the values or the forces in our free body diagram step by step as we move through each work so that we can use our free body diagram to calculate or to determine the value of theta as we calculate each work. So if we put this onto our calculator, we have 50 times 5 times cos of 30, and that is then going to give us a value of 216.51 joules. And this is a positive value, which means that energy is being added to the object. Now, let us try and calculate our value of the work done by frictional force. Our value of frictional force is 20 newtons. Keep in mind, we're not going to put negative 20, we're only writing the magnitude. Times our displacement, which is 5 meters, times cos of our value of theta. Now we need to determine what is the value of theta, or what is the angle between our displacement and our force of our kinetic friction. Now, let's draw our kinetic frictional force. So, as you can see, there is a 180-degree angle between our kinetic frictional force and our displacement, because kinetic frictional force is in the opposite direction to displacement, and it forms a straight line on our free body diagram. So this is going to be 180 degrees, and that is then going to give us negative 100 joules. Because we ended up with a negative value, that means that kinetic frictional force is removing 100 joules of energy from the object. Next, let's calculate the work done by normal force. And we know that normal force is equal to our gravitational force, or Fg, and that is equal to the mass times gravitational acceleration. So that is mg times displacement times cos of theta. Now, something important to take note of is that normal force is perpendicular to the surface on which the object is traveling, and our surface is parallel to our displacement. Therefore, normal force is perpendicular to our displacement. You can also see that in our diagram. So let us put in our normal force. all we do is we put our normal force perpendicular to our displacement as per our diagram, and that is 90 degrees. We know that cos of 90 is 0, so multiply this whole thing by 0, and we have 0 joules because our normal force is perpendicular to displacement, which results in cos of 90, which is 0. Now, let us try and calculate the work done by Fg, the work done by our gravitational force. We know that the work done by Fg is equal to our force Fg times our displacement times cos of theta. And Fg is calculated as mass times gravitational acceleration. So that is going to be the mass times the gravitational acceleration times displacement times cos of theta. Now, because normal force and Fg form a straight line, and the angle between normal force and displacement is 90 degrees, that means that the angle between Fg and displacement is also going to be 90 degrees, angles on a straight line. Alternatively, you can think of it as displacement is perpendicular to Fg. So let's put that in. We then know that the work done by Fg is going to be 0 because Fg is perpendicular to displacement, which means that cos of 90 will be 0. And if we want to put Fg in our free body diagram, we can just have a line going straight down because Fg acts straight down. And that is our free body diagram. Now, we needed to calculate the net work done. So, because we're using the first method, all we are going to do is add up all of the individual works that were previously calculated. Let's substitute them in. So I'm going to leave out the two zeros because we know 0 is nothing, so it would be pointless to put it in. And we therefore have our net work done on this object as 216.51 minus 100 joules of energy, which gives us 116,51 joules. And that is a positive value. Let us now use the second method to calculate for work net. So in this method, we're going to use the formula work net equals F net times displacement times cos of the angle between our displacement vector and our net force. Our first step is going to be to calculate the net force. So the approach that we are going to take is similar to the approach that you've used in Newton's second law of motion, so you should already be familiar with it. So previously we did not use the components of our applied force. But in this specific case, we are going to use the components of our applied force because in order for us to calculate F net, we need the components. Specifically, our horizontal components because we are dealing with our horizontal forces. So we are going to use FAX or the applied force in the horizontal direction. Our formula is F net equals, now the only two forces that we have acting in the horizontal plane is our horizontal component of applied force plus our kinetic friction. Now we need to decide which is going to be positive and which is going to be negative. And yes, in this specific case, we are going to take into consideration the direction as opposed to what we previously did. Previously, we were calculating for a scalar quantity, which was work. When we're calculating for a scalar quantity, we don't need to take into consideration direction. Whereas in this case, we are calculating for a vector quantity, which is F net. So we will in fact take direction into consideration. So we are going to take right as positive. That means that our horizontal component of our applied force will be positive and the kinetic friction will be negative. So let us now try and calculate for FAX. So our FAX value is going to be equal to our applied force times cos of 30 degrees. Now the reason we're going to use cos of 30 degrees is because FAX is adjacent to theta or adjacent to this 30-degree angle. Whereas if we are calculating for FAY, which would have been the opposite side, which would have looked like this, we would have used sine. So let us now calculate for the horizontal component. Our applied force is 50 newtons, and that is going to give us a value of 43,30 newtons. And because that is positive, it is in the right direction. Now that is going to be important when we calculate or when we determine our value of theta. So let us now substitute this into our formula. Now, our value of kinetic friction is going to be negative 20 newtons because it is in the left direction and we took right as positive. Therefore, our value of F net is going to be 23,30 newtons. Now let us try and find our value of work net. That is going to be F net times displacement times cos of theta, whereby theta represents the value between our displacement vector and our net force. So let this represent our object. Let us now draw our displacement vector, which will be in the right direction. And we can also draw our force, or rather our net force, which will also be moving in the right direction. And as you can see, our net force and our displacement are in the same direction and on top of one another, so there's a distance or an angle of 0 degrees between them. So theta would be equal to 0 degrees. So this is then going to be work net equals our net force, which is 23,30 times our displacement, which is 5 meters times cos of 0 degrees. Once we put this onto our calculator, we will end up with a work net value of 116,51 joules. And as you can see, that is the exact same value as our previous method. So irrespective of which method you use, you'll end up with the same value. So let us quickly go through the methods that we've used. In our first method, we calculated the individual works based on each force that was acting on this object. Now, when we're using the first method, we do not need to take into consideration the components of the forces. We only take into consideration the forces themselves. And when we substitute our values of our forces into our formula, we do not take into consideration the directions of the forces, so we will only substitute the magnitudes. We will not substitute a negative or positive sign which indicates direction. Because we are calculating for scalar quantity, which is work. When we're using our second method, we first calculate net force, which is a vector quantity. That is why we will take into consideration the directions and the components of our applied force. Once we find F net, we can substitute that value into our work net formula, and then we need to find the angle between our displacement and our F net value, or our F net vector, sorry. So once we find the angle between our displacement vector and our F net vector, we can then substitute that in place of theta, and that will give us our work net. So it does not matter which method you prefer to use or which method you actually use, both methods will result in the same answer. So that is the end of our video for today. In our next video, we'll have a look at objects moving on an inclined plane. So objects moving up the ramp or down the ramp, and we can then break up those objects into the forces and calculate the work done on each force. And we'll also have a look at a few examples relating to that. So, thank you guys for watching. Hopefully, it was beneficial, and I hope you guys enjoy the rest of your day.